Okay, in the last section, we modeled circular motion on the unit circle, and we investigated different locations around the unit circle. Now we're going to go from looking at circular motion to then taking that circular motion and looking at a trig function one at a time in a function which includes time. And so we're going to do circular motion over time. Okay, so let's look at y equal to sine x to begin. Well, remember before we talked about how sine of x corresponded to y value, and then we could of course evaluate those as we went around the unit circle. Well, the same thing's going to happen here, and we're going to go from this circle here on the left, and then we're going to go to more of what's called a sinusoidal graph here on the right. Okay, so let's take it one at a time. What is the value of sine here when I start here at 0? Well, my y value is sine, and so I'll be at 0. So if I were to plot that point here on this graph, that would be 0. Okay, and this is my dimension of time. Okay, now let's go now from this location to now this location as positive movement would go. Now what's my sine value? Well, again, sine corresponds to y, and at sine there y is 1. Let's keep going around the circle. How about at pi? Well, at pi I'm at my y value here that corresponds to sine is 0. And 3 pi halves my y value, -1. And back at 2 pi, I'm back to 0. So if I went ahead and drew that shape, well, now we have what's called a sine graph, or a sinusoid curve. So we've taken that circular motion, and now we're going to put it on an xy plane with time here, and of course y here. Y is a function of time. So as sine goes in a circle, it also creates what's called a wave. Okay, and this wave has certain properties. This is what's called your A, or amplitude. From the midpoint to the highest maximum point there. Okay, so our A here is 1. And it's going to also be defined by this idea of how far did it travel to make one complete cycle. Notice we started here, or one revolution. Now, from 0 we went up to 1, and back to 0, and back down to -1, and back here. That's the completion of one cycle here at 2 pi. So this is what's called the period. And the period is the time it takes to complete one revolution. Notice I went up, down, and back to where I started. Okay, so this idea is period. This horizontal distance to make one revolution. And then the distance from 0 to the edge is called our amplitude. In this case is 1. Okay, let's look at our general sine function, y equals a sine b of x. And we're just going to focus on sine to begin, and then after we are comfortable with sine, we'll go on to cosine. Okay, so our amplitude is always found here. In front of, say, the sine of bx. So a sine of bx, a here is our amplitude. The absolute value of a, in this case, if nothing is showing, say we're looking at this function here, well, we assume then it's a 1. Okay, and this is the one we just worked on, and I'm just going to go through it quickly, and then we'll do another example on top of it. Okay, so my amplitude, the absolute value of 1 is 1. And we'll get into the definition of amplitude again here in a second. And also period. Now then our period is 2 pi over the absolute value of b. And that would be, well, 2 pi. And again, if there's nothing here showing in front of b, then, I'm sorry, in front of x, which would be b, then we assume it's 1. So 2 pi over the absolute value of 1 is just 2 pi over 1, which is 2 pi. So if I maybe had the function of y equals 4 sine of x. Well, y equal to 4 sine of x, we know we have an amplitude, which is the absolute value of a, would be the absolute value of 4, which is 4. Well, that amplitude corresponds to vertical stretch or shrink. It's out front of our function and multiplied by the whole function. In this case, it's a vertical stretch of 4. And then again, our period, which we said we're going to keep the same here, would be 2 pi over the absolute value of b. And b is just 1, so that'd be 2 pi over 1, which is 2 pi. And again, we're just keeping it like we have here. Okay, so when I went to, say, evaluate these, and I made my xy table, I know at 0 I should still be at 0, and say pi halves. Let's just do pi halves, for example. So y equals 4 times the sine of pi halves. This is where my knowledge of the unit circle will help me. The sine of pi halves, or a sine of 90 degrees, I know corresponds to y, and my y value at that location is 1. 1 times 4 is 4. And then I go through my other locations. Let me just continue my xy table here. Pi, 3 pi halves, and 2 pi. And I'd be back to 0, down to negative 4, and back to 0. So when I went to graph it, here's the points I would plot now instead. And my scale's just a little off. I want to be able to show all of it in here. Well, okay. So notice this has the same period length. That's the distance from here to one wave being completed, one cycle. But it's got a different amplitude. Well, our original had an amplitude of, well, 1 because it wasn't showing. And then our transform function had 1 of 4. So in other words, it had a vertical stretch of 4. And that's just what it did to my signal wave here. It stretched it by a factor of 4. So notice it's taller and thinner, this light purple one is, than maybe our original darker purple one is. Okay, so the same transformations we're used to looking at on other graphs will apply also on our, say, sine graph, which is what we're looking at now. And what do you imagine if we had a vertical shrink would do? Well, a vertical shrink would make this, of course, maybe lower than. So if I had a vertical shrink, and of course we'd have to come up with a function, but it might be lower. Still going through the same locations, but shrunk from our parent function there. Okay, so we can have vertical stretch or vertical shrink of our sine function. Okay, in our next example, we'll look at more thoroughly amplitude and period, and let's look at that next.